Good morning. We have had 6 lectures, I think, in statistically speaking so far, and today is number 7. And actually today we're going to cover some of my favorite topics in statistics. And part of that is because we spend an awful lot of time thinking about how we do measures of variance across replicates here and replicates there to figure out which things are different. You know, the classic Ttest scenario. But there are lots of times when we don't have replicate studies to work with. Instead, we have sort of a singleton experiment that we need to make sense of. A lot of these boil down to something we call a contingency table. So today is all about the interesting things you can do with contingency table kinds of problems. However, I wanted to note that there's a bit of a debate in the statistical community. There are the Bayesian statisticians and the frequentist statisticians, and they have kind of different attitudes about things. The key principle associated with being a frequentist is that you care about the data in front of you. You don't have prior expectations of whether this result is more likely than that result. Typically, your focus is on the null hypothesis, and we've talked about that in the context of Ttest and Utest already. This idea that there is no difference. So are the data that we've observed plausible under that null hypothesis, that there is no difference? So I thought this cartoon was a useful little joke, because the first thing that you hear when you encounter a Bayesian is a discussion about being informed by prior experiments. In fact, by having prior probabilities associated with particular events. So in this case, we have a frequentist and a Bayesian sitting down. You often find these jokes told by Bayesians, not frequentists, but that's fine. So I still don't know why we have this debate over whether a frequentist or a Bayesian approach is the right one every year. The frequentist replies, I know, it's a bit passé. And so the other person says, you want to toss for it? You have a little coin all set, you want to toss for it and figure out who wins that way? And the frequentist replies, sure. So wait a minute, is that a fair coin? Do we know whether this coin gives an even mix of heads and tails? The Bayesian replies, maybe it is and maybe it isn't. Being a jerk already, that's okay. And then the frequentist says, that's tricky. And upon reflection, well, okay then, taking all these things into consideration, I call heads. The Bayesian replies, aha, a prior construction, Bayes wins again. Ah! So you see the problem here. Most of the time, when we're talking about something like a coin flip, we're assuming an equal probability of heads or tails resulting from that. The Bayesian knows whether or not the coin being used is loaded in favor of one outcome or the other. So this key phrase that you see coming out of the frequentist's mouth is the concession to becoming Bayesian. Taking all these things into consideration. That's a key phrase for us. Taking prior knowledge into consideration is relying on a given. And so that is effectively saying that frequentists are actually Bayesians. They just don't want to admit that they know something about the backgrounds from which their data come. All right, so I thought it was funny, first off, but the cartoon is actually illustrative of this divide that you'll find in Bayesian and frequentist thinking. Today's lecture comes down really heavily on the side of frequentist statistics. So we're going to start with a discussion of contingency tables, and we're going to use this concept of the Chisquared test of independence, which I've found a little hard to describe, and under some circumstances today we're going to nail it down on, because I think it's useful. From there, we're going to talk about the binomial and hypergeometric distributions. Those names sound a little scary, but we're mostly going to talk about flipping coins and dealing with a jar of marbles or a deck of cards. So hopefully that will make things feel a little simpler. And from there, we're going to move into one of the best uses of a contingency table, that is Fisher's exact test, or how to get away with one replicate and still put a p-value on something. So you don't have to have replicates to get p-values. So we started with this notion of the student's t-test, and I made some important qualifications about student's t-test. I argued that the numbers needed to be continuous and normally distributed. However, frequently we're working with count data instead, and counts are not typically Gaussian in their distribution because they're not continuous, they're discrete. They're 0, or they're 1, or they're 2. They're not 1.362, for example. And they have a lower bound of 0. You can't have less than that in a count. You can't have negative 1 counts. So the other thing is that you frequently get ties, and ties can really foul up the metrics that we compute from them as well. The other thing that I've written in here, it might seem a little prosaic. I've said that a 0 may be a measurement. So what am I talking about here? Frequently when we see certain values in a table that code for non-numeric things. So we might have a 0 or a missing or just an empty value in a table, and that means we don't know what this measurement should be. It's essentially a not applicable. So frequently you'll see someone using a 0 to code for something like that. But once you're dealing with count data, frequently we see that 0 is actually a measurement. There were 0 counts for this particular cell. Hello, welcome. All right, so counts have sort of different properties, is what I'm saying. They're not normally distributed. They're not continuous, and so we need to have some statistical methods that have count presumptions about them, not just continuous. So a contingency table is one of these basic ways to do this. So you've sometimes seen them called cross-tabulations, or crosstabs. So it's an example of how samples divide across categories. Now, the example I'm starting us off with is kind of a grisly one. I believe using real data helps us to illustrate real problems in these. So what I'm using are data from worldlifeexpectancy.com, and I chose the set of people who are about the ages of graduate students, hope you don't mind, ages 25 to 34, people in the United States who died from various causes. So we're looking at the cause of death for people between the ages of 25 and 34 in the United States during the period of a year. I think these were like 2015 data or something like that. So we have this body of people. Over here on the table we see it's 28,300 people in the United States who died between those ages in the course of a year. So each person amounts to 1 count in this table, and that is actually an important property. We don't want a table where one event leads to 2 different counts being produced. So if the person were female, they added to a count in the top row. If they were male, they added a count in the bottom row. If they died of poisoning or suicide or road traffic accidents or homicide or other injuries or endocrine disorders, then they added to a count in that column and that column only. So many events here, but all recorded in this table in that way. So there are other categories that exist here. There are, I'm sure, for example, there's probably one person crushed by a piano, for example. We're not going to include small count categories here because having sparse data, having very few counts in a cell, actually leads to some problems with some of these analyses. Later on, when we talk about Fisher exact test, we're going to talk about a test that actually works really well, even when you have very few data points to work from. But for now, we're focusing on just the top 6 categories overall for things that kill people. So poisoning, does this mean that American young adults are particularly good at drinking drain cleaner? It's the #1 cause of death for people between 25 and 34. So does that mean that we need to develop young adult proof caps to prevent people from drinking drain cleaner? No, they're not drinking drain cleaner. What kills Americans ages 25 through 34 by poisoning? Yes, illegal drug use. Meth, cocaine, LSD, whatever, overdoses of all sorts get coded in this database as poisoning. So we'll just take that into account. So a lot of Americans of this young adult class dying of drugs. Suicide kills a lot of people in this age group. Road traffic accidents. Has anyone ever been in an accident on the roads here?
Sorry, I want to ask you something.
Oh, sure.
Does poisoning involve food poisoning also?
I don't think food poisoning is counted there. I mean, you get really sick from food poisoning, but most people in the States wouldn't die of that in this age bracket. But how they define each of those brackets is worth talking about. Yeah. Well, these are arbitrary data. This is just the categorization used by this website. So we see that we've got some deaths now. What else strikes you as really weird about this table? What about the difference between the rows?
So how about males and females?
Right. So I had a really interesting chat with my doctor as I just became a professor. I was, let me see, that would have been 2005. So I was 32 years of age. My doctor said something really weird to me. He said, "You are a young adult male. My goal is to keep you alive, because if you're alive, you are probably in good health." Isn't that weird? So, this is why we see that disease doesn't figure into any of these except the sixth most important category. Dying is a risk for a young adult male. Getting sick usually isn't the problem. So, we think about things like gun violence in the United States. We saw a pretty primo example of that this week. Yeah, kills a lot of people. But what about men versus women? Men are really good at dying. Really, really good at dying. So sometimes that means men engage in high-risk behaviors. For example, my stereotype of who gets in bar fights would be, oh, it's a drunk dude, right? Now that's a stereotype. So more generally, who do you send to war? Do you send young women to war in huge numbers? They do fight, and that's become more popular around the world as an option. But the reality is, most of the time the people we send out to do really crazy, dangerous stuff, like construction work on the side of the road, tend to have a higher penchant for being men. So yes, they die at a rate of something like 3 to 1. Crazy, huh? Now, do we find that the things that kill young people, men and women, are the same across genders? So you could answer that question in a variety of ways. You might try, for example, say a paired Ttest where you're comparing this value to that and so on. But that's not really the proper way to do it. The proper way to do it is through something that we call a chi-square test of independence. And it's a test of independence because we're asking, is there a relationship between the gender of people, between the rows, and the way that people die? All right? So let us figure out how to do this test of independence. So I started by throwing these data into Excel because it was easy to visualize the calculations here. So I had my raw numbers in Excel, and next I needed to figure out some proportions. So when I compared the totals, irrespective of how people died by gender, I saw a 24% and 76% split for females and males for this age group. So, like I said, 3 times as good at dying. Then, I took a look at the causes of death, and looking irrespective of gender, I saw that poisoning accounted for a third, suicide accounted for somewhere between a fourth and a fifth, traffic accidents were around a fifth, homicide was about 15%, 3/20ths, I guess, and other injuries were maybe 1 out of 50. I'm sorry, that's not right, 1 out of 25. So in this case, when I'm computing the probability for suicide, I'm computing that number irrespective of gender. So of all, 23% is suicide. So now, having filled in this short column and this long row, I'm going to convolve the two. I'm going to fill this cell, this top left cell, with the top row multiplied by the leftmost column percentage. Does everyone get that? So this is effectively saying, if the data are evenly spread across this contingency table, we expect that the values in the top row are going to be roughly 1/3 the values in the bottom row. And the same relationship holds for the columns. So we populate, we fill in these percentages in a way that reflects only the row column, the row totals and the column totals. Okay, so now we say that we have our estimates now of the percentage of these data. We multiply that by the table total. We had something like 28,300 people. So now we're going to multiply this table by 28,000, and out pop our ideal numbers. Okay? So we have observed values, and now we have expected values, and the totals are exactly the same here as they were in the top. But how the numbers distribute may be different. So are they significantly different? That's what the chi-square test is all about. So this is not an x, this is a chi. Everyone recognizes chi, right? So we've got chi squared is equal to the sum of the observed value at each cell minus the expected value for each cell squared divided by the expectation. We've seen formulations like that before. We've been looking at residuals and things like that. Frequently we see an observed minus an expected value, then we square it. In this case, we're summing those up after they've been normalized by dividing by the expected values. Now, we've mentioned degrees of freedom. We're not free of degrees of freedom even now. We must compute the correct number of degrees of freedom for this table. Helpfully, that degree of freedom is calculated for you in a lot of cases, but just so you know, it's the number of rows minus 1 times the number of columns minus 1. So how many rows did we have in our table? Two sexes, so yeah. Rows minus 1 is 1. So that one just basically drops out. How many columns did we have? 6. 6 top causes. So 6 minus 1 is 5. So the number of degrees of freedom we have is 5. We can compute this chi-square value. We can compute the degree of freedom value. Therefore, we can get a p-value. So I have in our R script the code that creates that table in R. And we'll walk through that after the lecture. When we compute the chi-squared value, I know it's using an x, just forget it, it's a chi. The chi-squared value is 477.34. That's our test statistic. Then we can look it up to turn that into a p-value by supplying the degrees of freedom, which was 5, we just computed that. The p-value that we get is less than 2.2 times 10 to the negative 16. So it's saying that the expected values are quite different than what I've expected. The observed values are quite different than what we expected. So I'm going to scoot back just once. What do you notice from a rank perspective in evaluating these data? Comparing, let's call our comparison just between men and women. So as we look at this, if you were to write down what is the most common cause of death for males and for females, what would you say? Poisoning?
Suicide.
Okay, 6683 is higher than any other value in that row. So number 1 is poisoning. For females, that value is also true. What's the second most common killer for men versus women?
Suicide for men and accidents for women.
Exactly. Yeah, so suicide and accidents are different ranks for men as they are for women. So that's already a pretty big difference. Suicide is number 3 for women. Accidents are number 3 for men. And we can keep pushing on down the road and find others. But we see things like other injuries. I assume this is like bar fights. I don't know. Well, some women get into bar fights too. Sometimes they do. So, there we go. So we can see then that if we glanced at the data, we would have kind of this sense based on ranks alone that the data are not producing the same ranks in men as they are in women. That would be how we would start to explain why we got a low p-value from the chi-square test of independence. Okay, now let us work into the fine world of the binomial realm. Who would like to be scribe for me? Are you willing to write down heads and tails for me? Okay, we're going to flip a coin 10 times. Would you be our coin flipper? All right, we're going to call the what is it? Wildebeest? What is that? The 5 rand coin? Oh wait. Should we call it an Urdu? It's kind of fun to say. Oh, there's what? Hemsbach. That's fun to say, right? I can't pronounce it. Okay. So we're calling that heads. Okay, we're just going to write down 10 hits. So, okay, Hemsbach, so heads. Tails. Tails? Heads? Heads? Tails? That's tails. How many have we got? Okay, 3 more. Tails? Tails? Are we sure this is a fair coin? All right, heads. Okay, great. Thank you very much. Need to have this for tips. That's very valuable. I'm always very jealous of my 5 gram coins. It's like, oh, I gotta hang on to these for the next parking card and so on. All right. So, if that's a fair coin, we assume that the probability of heads is 50%. So, given that null hypothesis, we might ask how many of these 10 coin flips we expect to be heads just by random chance. Yeah, so we flipped the coin 10 times. We got if we got 5, we would say, oh yeah, that's exactly what's in line. But how many did we really get?
4.
Just 4. So maybe I have a coin that's biased. Maybe I don't, right? I would like to understand this discrepancy between what I observed and what I expected. So the binomial distribution is your friend for this. But you have to satisfy certain requirements before the binomial distribution is going to be your friend. So we start with, the experiment is n trials. So in this case, we had 10 coin flips, so we know our value of n. That's an easy one to satisfy. Next, only 2 possibilities. Binomial is useful when you've got a heads or tails outcome. If you have more than that many outcomes, let's say we were rolling a 6-sided die or something, then we would need to use something called the multinomial distribution, not the binomial. We're not going to discuss that in this context. So we had only 2 possibilities, therefore we can use the binomial. Each trial has the same success probability. I can't do this with a model where my random device has changes over time in its probability of heads. All right. Are the trials independent? This is an important one because these last 2 aren't really going to hold true when we get to the next slide. The trials are independent here because just because I flipped a head last time doesn't mean I have a greater chance of flipping a head this time. I would also note that this means that if we had, well, how many tails did we have in a row there? We had quite a few, right? So I had 4 tails in a row that she threw actually. So does that mean that it was more likely that we would roll a tail the next time if we'd rolled 3 in a row? No. We know that that coin is independent, that it's not constrained to give the same result on the next throw that it did the one before. This is somewhat different than something like the weather, right? If you were writing down rainy day, hot day, whatever, there's some dependence between these things, that if it's raining at 11:59, at 12:01 the following morning, it's probably still raining. So there's this dependency built in. So that's a way in which trials may not be independent. In this case, the coin flips were all independent of each other. So we have this distribution, the binomial distribution, which is very handy for us. So I've set up a model where I've used what's called the sequence operator. So sometimes you want to specify a sequence of numbers in R. And so here I'm saying I want every integer from 0 to 10. And it's going to spit out how many values will there be in this x vector? 0 to 10? Yes, how many different values is that? Good. It's 11 values, not 10. This is something in computer science that we call a fence post problem. A lot of people think if they set up a variable, say from 0 to 5, that they get back 5 values. But you have to remember 0 is also one of those values. Good catch. Okay, so we have the 11 values ranging from 0 to 10 stored in x, and then we just pull the value off the binomial distribution we pass in these 11 values, and it's going to pass us back 11 probabilities. So we've specified that the total number of throws of a coin is 10, and the probability for each of these that we're working with is 0.5. So yes, we do see the result we expected, that the most common the highest probability event is that we would get 5 heads out of 10 throws. Is it a lot more likely that we get 5 throws than that we get anything else? No, it isn't. This value, we can look up what it is exactly, but this value is only about a quarter. Only about a quarter of the time when you flip a coin 10 times do you get exactly 5 heads. The value for getting 4 heads, or the value for getting 6 heads, in fact, are identical. In this case, because it's a 0.5. So we can see that if we wanted to account for the middle half of outcomes, we would really need to extend out to 4 and 6. Is it possible that I get 10 heads in a row? Is it possible?
Yes.
Yes. Is it probable? No. Now, as a frequentist, I immediately think to myself, well, if each of those events has a probability of 1 and 2, and I've got 10 such events, I want to know how common these least likely outcomes are. So, in this case, it is equally likely that I would have 10 heads in a row as that I would have 10 tails in a row. And both of those I would think are pretty remarkable. So 1/2 raised to the 10th power is the same thing as 1 over 2 to the 10th. And then there are two such outcomes that I would care about, so I would double that value. So that's what these very, very low values here are on the extremes. All right, so we'll investigate this a little bit as we run through the example later. All right, now, the hypergeometric distribution is a bit tricky. Now, I've got an example that we're going to work through, but at the moment, I would like to bring out one of my favorite props. This is a candy jar, first off, that someone brought for the biomedical informatics people who are part of the mass spectrometry facility. So she brought this huge bottle of candy and just set it right outside my office in my second year as a professor. And I've used this jar now for years. I loved it so much, I stuck it on the crate of stuff to come across the ocean, and so I still have it. These marbles were produced by the Moon Marble Company right outside Kansas City, where I grew up. So this is a very sentimental jar of marbles. I like having my jar of marbles when I'm talking statistics, because statistics has so many things like this. I bring out this jar of marbles at the moment because I want to talk about this concept of replacement. Replacement is a very big deal. Before, we said that the trials of flipping this coin, goodness me, were independent. If I draw one marble from this jar at random, and put it back, and then grab another marble from the jar, put it back, and then grab another, I'm in a replacement situation. That means that the trials pulling from the jar are independent from each other. If, however, I pull out a set of, say, 10, I don't know how many this is, it's more than 10, it's more like a dozen. I've now grabbed a dozen marbles from this jar. There's no possibility that I'm going to count any one marble twice. All right? If I have drawn 3 black marbles from this jar, the probability of my subsequently drawing a black marble has dropped because there are fewer left for me to draw from. Okay? So this replacement issue is a very, very big deal, especially when you get to very small numbers of things. So if I had only 10 marbles in this jar, 5 of which were black, and I drew out 5 marbles, if one of those marbles is black, the probability that another marble is black has dropped as a result. Okay? So that's replacement. Now, we can also apply this to like a deck of cards, and I brought one of those along for our next slide, but for now, we'll just talk about this. Now, I have an awful lot of parentheses over here. People remember your math classes, so we all remember math very well, right? You love math. You kept awake every last moment in class. Not so much. Okay, that's fine, that's fine. What do these odd parentheses with a number on top and a number on bottom represent? Ooh, okay. Silence on this one. Those represent combinations. Combinations. So, we will not get into the math at the moment. Suffice to say it involves some number of factorials, etc. So when we look at the math of doing a probability from the hypergeometric distribution, it's awfully nice if you can leave that math to some software to do it for you. Because otherwise you end up having to do a lot of computations unless you really think carefully about how to reduce these fractions. So let's start by saying that we need to have, we're going to have the jar. I want you to think of this is the population, and I have a sample. Okay, so I have the values that I've sampled out of the population, and that's kind of a separate entity than the population itself. So jar, hand. Next, I have successes and I have failures. Okay, so in this case, I'm going to define drawing a black marble as a success and drawing a white marble as a failure. So I've still got two outcomes. Remember we were all talking about heads and tails in the last case? Now I've just changed the definition to say that the marble color reflects whether it's a success or a failure. So K is the number of successes in the population. So in this case, if I know exactly how many black marbles I've got, I know how many successes there are in the population. That's K. Little k is the number of successes in our sample. So having pulled out a set of marbles, I say I have 1, 2, 3, 4, 5 black marbles, therefore I have 5 as my little k value. We have the number of all items in the population, the total number of marbles in this jar, and we have the total number of items that we sampled from that population. With those 4 numbers, we can compute the probability that this particular outcome would have come about by running this bit of math. So let's look in practice at how this plays out. Do we have any card players here? No one plays cards? Oh, good, good, good. All right, so yeah, I have my standard deck of cards here. This is also a very well-traveled card deck. When I was in high school, we used to go to math competitions, and we would play spades from about 6:30 in the morning until about 6 p.m. at night when we got back from the math competition, an obscene amount of cards. And so I always love the game Spades. So you start with your 52 card deck, and you deal them out to 4 players. So with 52 cards, how many, do I have the same number of cards in each suit? In a standard poker deck? I do. Yeah, I've got 13 clubs, 13 spades, 13 hearts, and 13 diamonds. So standard card deck. So if I'm dealing those out in spades, the cards you care about most is the set of spades. If you've got a lot of spades, you're deep in trump, and you're really going to hurt other people when it comes time to play out the hand. So having a lot of spades is really good, and having very few spades is going to be very bad for you. Okay, so having received cards, what is the probability that in your hand you're going to have 13 spades? I've always wondered this, right? So all of the cards in the deck have been divided among 4 people. What's the chance that one of them received all of the spades? Okay, so let us say we're working with Monique, right? We've dealt out the cards. What are the chances that Monique herself has all 13 of the spades? We're now going to define the number of spades in the deck, the number of cards that she has in her hands that are spades, etc. Now, the way that R handles these values is a little different. You can see that I'm going to feed it, the function I'm going to use is another one of these probability functions starting with D, the probability density function. So I'm going to do the density function for the hypergeometric distribution. I'm going to pass it my vector from 0 to 13, because those are all the outcomes. You could have 0 spades in your hand, and that would be a very, very bad round for you. So then we have an M equals 13. So that's the number of spades in the card deck. They have you specify the number of failures in the deck as well. So here I've got 52 minus 13 gives us 39 cards in the deck that are not spades. And then the number of cards that I sampled out of that into my hand is 13 as well, because each player receives 13 cards. So here we can say that the probability of getting 0 spades is pretty close to 0, but possible. May happen every 50 games or so. The number of times you get 1 spades is a little more likely, 2 spades even more likely, 3 spades is the most likely outcome, and then it falls off pretty sharply. The probability that you end up with all of the spades in your hand is vanishingly small. So all of that comes out of the hypergeometric distribution. Now, one of the things we're going to contrast with this is, well, we're going to be talking about the Fisher exact test in just a minute. And the Fisher exact test is a cited p-value. What these represent is the probability of this particular outcome taking place. Just this one outcome. So, are there any possibilities in dealing out cards that are unaccounted for here? Right. There are no others. You can't receive 2.5 spades, for example. That's not possible. You're going to receive an integer number of spades. 0 is one possibility. 13 is the most you could possibly receive because you've only got 13 cards, and coincidentally there are 13 spades in the deck. So these are all of the outcomes. These are the probabilities of individual outcomes. And so one of the magical things that results from this is that if we add all of these values together, we get what value? One. Well, 100% or 1, yes. Yeah, so when you have all of these individual probabilities and you add them together, I'm going to scoot back one here, scoot back 2. Remember, we looked at the probability of getting some number of heads from flipping the coin 10 times. If you sum these together, you get 100%. You get all of the possible outcomes. Similarly, if you sum all of these values together, you still get 1. So this is a probability density estimate. When we look at Fisher's exact test, we're going to be looking for the summed probability of all outcomes that are less likely than this one. So if you were asking, what is the probability that I have 4 or more spades? That's a bigger probability than saying, what is the probability that I get exactly 4 spades? Does everyone see that?
Yeah.
Okay, let me work through the logic on that one more time. The probability that I get dealt exactly 4 spades is this number exactly. The probability that I get 4 or more spades is the sum of this, plus that, and so on, through all of those more extreme possibilities. So I want you to have this concept in your mind. A point probability is different than a p-value, because a p-value generally has a summed property to it, that we're asking what is the probability of this and the more extreme outcomes. Okay, from there, we come to a very different kind of Ttest. The origin of this problem was described by R.A. Fisher. I mentioned he shows up a lot, didn't I? Right, so R.A. Fisher told this story in a book that he wrote that ended up becoming a really hugely popular one, and it is called the lady drinking tea problem. Now, I learned this morning that that's actually kind of disingenuous. The lady drinking tea is not some sort of socialite who had no idea of science. She was actually a researcher at the same institution as the one where R.A. Fisher worked. And they had this little interaction in a tea one afternoon as they sat in their kitchenette at the Rothamsted facility. Dr. Bristol, not lady drinking tea, Dr. Bristol was offered a cup of tea by R.A. Fisher, and she said, no, you didn't make it right. She said, no, I don't drink tea when the milk was added to the tea. What I want is to see that the milk has been poured into the cup first, and then we add the tea. Well, that's odd, isn't it? Now, I didn't grow up in a tea drinking culture, so for me, the idea that someone could tell whether the tea was added first or the milk was added first sounds ridiculous. Who could do something like that? That's clearly someone just being very haughty. However, she felt very strongly about this, and so he started thinking about how could we discern whether or not she really has the ability to discriminate whether milk was added first or tea was added first to her cup. And out of this came Fisher's exact test. The goal being compute the probability that by random chance alone, someone would discriminate this well or better. Or better. You heard that, or better? That means we're summing together probabilities. Okay, so here's Dr. Bristol, a photo that that one of the archivists at Rothamsted was able to provide. So, he created a test to evaluate whether or not she could really tell the difference. Prepare 8 cups of tea, so we're going to keep her busy drinking tea for a little bit here, where 4 of them had the tea poured in first, and 4 of them had milk poured in first. Could she correctly separate them? So she was going to be provided information about this test. She was going to know in advance there are going to be 8 such cups, and only 4 of them are milk first, the way she likes it. So her goal is to be able to take a sip from each of these and say, yeah, that's definitely milk first. Ooh, that's definitely tea first, etc. She has to make her judgment in advance, knowing how many of these were good, were milk first. Now, let's talk about the way this discrimination works. Do we treat it as equally good if she says these 4 were all milk first, only to discover that those were the tea first ones? That's perfect negative discrimination, claiming these 4 objects are all type A when they're all type B. So there's a sidedness to this examination. We're going to ask, not only does she discriminate them into 2 classes properly, but she knows which class is which. Okay, so this was the struggle, the comparison that they put together. The book does not record whether she was able to do this correctly or not. So you'll sometimes see people say that yes, she definitely did it, or no, she definitely didn't. But I want to show you some of the hardness of this challenge that's been put together. So when you have 4 cups of class M and 4 cups of class T to choose from, there are 70 different combinations of cups. So let us imagine that she has selected 1, 2, 3, 4, these 4 cups as being tea first, when they're actually milk first. That represents a fail, 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 fail in the sets that she has declared are milk first. There's only one way that you can do that you could make that particular error. So there's only one permutation that accomplishes that. There are 4 different ways, in terms of the order that you pick these out and call them tea first, that you can get this wrong the other way. And you have to multiply that by 4, because which one you claim is milk that is actually tea could change. So we see that there are 16 outcomes there. There are 36 different ways that you could get this mixed 2 by 2. That's the most likely outcome. If she really has no idea which ones were milk or tea first, this is the outcome you'd expect, because actually more than half of the possible outcomes correspond to this having 2 of each class mixed together. All right, by the time we get down to option 3, where she's gotten a correct hit on 3 of the 4 that she calls milk first, we see that there are still 16 ways that could happen by random chance. So the cards are really stacked against her. The only outcome that's going to produce a p-value less than 0.05 is one where she says exactly, these 4 are all milk first, and these 4 are all tea first. And she gets it perfectly right. It's the only outcome by which a p-value of less than 0.05 results. Okay, so what else do I need to do? So the null hypothesis is the only one really at stake here. She has no ability to differentiate between milk first and tea first. The probability evaluates the probability that by random chance she would do this unlikely a result or more in one direction. So how does it play out? Now I used a GraphPad Prism website to work out the examples, but the result is exactly the same whether you do it in GraphPad or R. I just kind of like the visualization, so I used this from their website. So this first result, I wanted to return to this concept of the contingency table. We started the lecture with that, so let's get back to it. We have truth represented by columns. We know, we have a label that's been hidden from Dr. Bristol, whether this cup was tea first or milk first. That is the truth. Compared to that, we have a judgment. So Dr. Bristol's judgments about the tea will be represented by the row where that count appears, and our knowledge of whether it was really milk first or tea first is represented by a column. So in this top case, we have the very best result Dr. Bristol could possibly achieve. We have that every truly tea first was judged tea first, and every milk first was truly judged milk first. Was correctly judged milk first by her. So this is the contingency table where each cup, remember there are 8, contribute 1 count to our contingency table. Down here, we have the one failure route. There were 3 that were really tea first, that were judged tea first. There were 3 that were actually milk first, that she judged as milk first. And then there's 1 of each that got shuffled between the 2. There was a pair of cups that she had incorrectly partitioned between milk and tea first. Look at how that p-value rises. It becomes very distant from this. So there's only, out of the 70 random shuffles of these cups into classes of 4 apiece, there's only 1 outcome that can possibly give her a significant p-value. All right. In R, it looks a little like this. Now, I think we'll walk through that code in just a minute when we do this in the tutorial. But for now, I want you to realize that these data can be tested through a Fisher exact test to give us an exact probability that this particular outcome would happen, or something more extreme, by random chance. And I want to note here that I've specified that there's a polarity to this. We're not interested in knowing that she can partition to tea first and milk first perfectly. That's not the only part of it. We want her to know which of those sets of 4 represents milk first and which one represents tea first. If she has those reversed, it's a complete error in the separation. So that allows us to use a one-sided hypothesis. And that one-sided means that she's going to have to know which cohort to switch. All right, so we like replicates. Estimates of variance are a really big deal, and we sure do like them. There are times when the study design does not lend itself to a replicate structure. So it is possible to compute p-values even when you don't have replicates to work with. Some of these are good examples, I think, of how situations where that arises. The binomial and hypergeometric distributions are key to understanding these 2 outcome trials. I mentioned the multinomial is useful when you're trying to deal with something with more than 2 outcomes. Maybe you have one of 6 colors that come from a particular experiment. For something like that, multinomial rather than binomial is appropriate. Similarly, the hypergeometric is cousin to the multivariate hypergeometric distribution, where you can deal with count data where more than 2 outcomes are listed. Generally speaking, the 2 that you learn about are binomial and hypergeometric. Fisher's exact test is very useful when you are trying to decide whether this discrimination is a random event or not. So I hope that today you learned a few tests that are going to help you, especially in cases where you have just a few counts that are distributable in a contingency table. Okay? Now, how much time did I leave myself for a little look at the R behind us?
7 minutes.
7 minutes? Have I been rattling that long? It's terrible. Well, let's pop over to these examples then without more time. All right, I want to switch to duplicate. Okay. Well, I have our code back here. Code. I see that the table is. All right. There's not a lot of R code here, but I'll try to walk through it. First off, when I created this mortality matrix, at first I started in Excel because I wanted to visualize how we came up with our expected values starting from those raw data. In this case, R is able to do all of that work for us, really. So starting at this top, you see that I'm force feeding it the numbers. 2651, 1347. So here I've just given it the 6 numbers for women, followed by the 6 numbers for men. How does it know how to sort this though? I had to tell it that this is a 2-dimensional table. So we see n row equals 2 is forcing this to give us 2 different rows, and the number of columns equals 6. Now that by row equals t is actually doing a lot of work, because I've given it this vector of 12 numbers, and I've told it I'm going to give them to you in row order, not in column order. So if I was giving it the numbers 2651, 6683, 1347, 5222, then I would not need this by row equals true business. So I'm populating a table in this first number, in this first line that just continues out for a stretch. The other thing that I'm doing is giving that table names. So I'm passing it female and male, the row names first, and then poisoning, suicide, road traffic accidents, homicide, etc. next. So when I run that code, I'm going to create a table from those values. Okay. So what does it look like? I can just say mortality, and you see that the structure in here is already set up with labels on those 2 rows and column headings that relate to the contents. I see that was cutting off the left edge. I'm going to scoot that over a little bit. There we go. Did that code run correctly for you? Oh, good, okay. So when we return to this, we can do kind of a nasty little bar plot to see if those values look right. And we see that having applied these names is actually very useful because the plotting function takes those labels into account when it's producing its plot. And of course, it's quite obvious when you look at the bar chart that these white bars are a lot taller than the black bars. That's showing that the death rates for men in general are higher than those for women. Okay, the chi-square test is very easy to perform. You just pass it the table as an argument. So let us do that. You can see how it pops. No delays. It's just a very quick assessment. So it's able to compute these expected values, subtract the expected values from the observed values, square them, sum them up, and translate that to a p-value very, very quickly. All right. I think I showed this code in the course of the lecture. So what does x look like? X is just a vector of 11 different values, 0 to 10. And then I have a plot that I'm generating from it. And that looks like this. So I've already shown that plot to you in the course of the lecture. This is the code that runs the hypergeometric distribution. Not very different. So we could restructure this in a different way and use the jar of marbles as an example. We could say, what's the probability that in sampling 10 marbles out of the jar that had 100 black marbles and 900 white marbles, that I would have 7 or more by random chance? I could compute that by summing together the probability for 7, 8, 9, and 10 marbles and sum those together. Okay, so we used the playing cards as an example for that. We could build it off the jar of marbles as well. Now, I wanted to walk through the code for these a little bit. This is the Ttest, the Fish's exact test examination. Oops. All right. So let's talk about this function right here. So I'm creating a matrix. Again, I'm feeding it the values that are to appear in this matrix. I'm giving them 4, 0, 0, 4. I tell it that there are 2 rows. By that, it infers that there are 2 columns because there are 4 values. Everyone gets that. If you feed it 4 values and say put them in 2 rows, it assumes 2 columns. The names that it gives are judgment on one and truth on the other axis. And truth and judgment each have values of milk or tea first. So when I look at the matrix that is produced, I call that one tasting, right? It sees that the columns will be called truth, milk or tea, and judgment will appear as the label for the other axis, milk or tea. All right. The Fisher test is a pretty straightforward application. In this case, I'm using the one mistake approach. So I've forced it to be one-sided. See, the true odds ratio is greater than 1. So I'm forcing it to, forcing her to know which cohort is which as well. And in this case, we see that if she makes even a single error, she ends up with a p-value that's not significant. The example for making no mistakes looks like this instead. So the tasting matrix looks like this. For all of the truly milk first, she judges them to be milk first. For all of the true tea firsts, she judges them to be tea first. That's the only perfect score, really. And we see that the probability associated with that outcome is only 1.4%. It's a really hard test in this case. So this is the Fisher exact test. It's a very good friend when you're trying to figure out which things are differing when you don't have replicates to work with. Okay, so I hope the concept of contingency table is pretty fresh in your mind. You have some notion of what kinds of data present themselves in that kind of format. I hope that you know why a binomial or a hypergeometric distribution is useful, and that you recognize this relationship that exists between the hypergeometric distribution and Fisher's exact test, because one is really just summing up values from the other. I know that our skills that we're going through are getting crowded out because I keep adding more and more slides as time goes by. I hope you forgive, and if you are trying to make some solutions in R and you're running afoul of problems, I hope you'll come chat with me about it. So we do have statistics next week. Today is the 4th? Today is the 5th. Oh, okay, well, so we do have class on the 12th, next Thursday, but we do not in 2 weeks. So I appreciate you giving me some time to pack for Russia, among other things. So, but I have enjoyed working with you on this, and I look forward to our lecture next week as well. Thanks, everybody.
Thank you.